All right, let's get started with lecture 6. So far in this course, we talked about wave-particle duality. We motivated the concept of the wave function, whose absolute value squared gives us the probability of finding the particle at different positions. We discussed the time-dependent Schrodinger equation, which governs the dynamics of the wave function. We talked about stationary solutions to this equation, so solutions where the probability distribution doesn't depend on time. And we talked about the time independent Schrodinger equation, which gives us these energy eigenvalues. And we did two particular examples. So we talked about particle in a box, and we talked about um, the simple harmonic oscillator. So today, what I want to talk about um, are expectation values, quantum expectation values. So plan for today. Operators and uncertainty. So as you may imagine, even when we started talking about the example of, let's say, the double slit experiment for electrons, quantum measurements, quantum observations they look pretty random, right? Even with the same wave function, every time you detect a particle, you find it somewhere else. So there's some notion of lack of certainty in let's say, the position of a particle. So we want to put that on kind of a firmer footing. So some of the things I want to talk about today, we've alluded to before. So we have some experience, for example, finding the average position, right? So we've already seen one expectation value of position. Well, we use the expression that, the average of any quantity is the sum over the quantity times the probability of that value. So for example, we had this expression that we used before. Let's say even that can be a function of time. So then the expectation value becomes a function of time squared times x, right? So times dx. So psi squared dx is the probability of being in a tiny interval of length dx located at x, and x is the value of x for that interval. So this gives us the average position. I can alternatively write this in a different way by noticing that the absolute value squared is the function itself times its complex conjugate. So I can also write this as psi star, the complex conjugate, which is basically changing every I to a minus I, times x times psi of x and t. By the way, the material I'm talking about today is discussed in section 5.8 of Harris. So that's one example of a quantum expectation value. It's basically an average, what you expect on average. If you repeat the measurement many, many times, every time you find some value for x, and the probabilities are given by this wave function squared. And if you take the average, it's going to be this quantity. So that's one example of expectation value that we've seen. We also alluded to operators, right? So for example, when we wrote the Schrodinger equation, so let's say time-dependent Schrodinger equation, time derivative of the wave function, was minus h bar squared over 2m, second derivative with respect to x, plus the potential times the wave function. And we said this is an operator corresponding to the kinetic energy, right? It may be useful to think about how we motivated the Schrodinger equation. Very early lectures, we talked about the de Broglie plane wave for a free particle. And we just wrote it using de Broglie relationships and kind of e to the I kx minus omega t for a plane wave that's traveling a sinusoidal wave. And we had relationships where k is 2 pi over lambda, omega is 2 pi times the frequency, and we knew that lambda is related to the momentum, so those are the Broglie relationships, and frequency is related to the energy. And furthermore, we said, well, if it's just a free particle, the total energy is the kinetic energy, p squared over 2m for free particle. So we used all of that to write the de Broglie plane wave, and then we guessed an equation that's satisfied by that plane wave, and it's basically the Schrodinger equation without the v term. And then the insight was, well, this is like a kinetic energy because when it acts on that plane wave, it brings down a factor of p squared over 2m. So in the same line of thought, we can consider an operator for momentum. And if that's like p squared over 2m, right? So it's somehow like the momentum operator. We can forget about 2m. So somehow we expect if there is some operator associated with momentum, when you square it, what it gives us is minus h bar squared second derivative, right, with respect to x. So it turns out that the momentum operator is kind of the square root of this, which can basically be two things. I mean, the square root of this, there are two things that when you act twice, you get this, right? So one is IH bar, first derivative. Another is minus IH bar. And it turns out that the correct one is minus IH bar, first derivative with respect to x. It's because for a wave that's, let's say, moving this way, has a momentum to the right, this gives the correct sign. So when you act with this on the de Broglie plane wave, you get a factor of p, the value of the momentum. So that's an important result, momentum operator. And if we start from here, the operator for kinetic energy, let's say k is equal to p squared over 2m. So kinetic energy operator, we can construct it, we can act twice, right? So it's going to be 1 over 2m minus IH bar first derivative with respect to x, minus IH bar another derivative with respect to x. So if this acts on, let's say, some function of x, what does it do? Well, minus 1 times minus 1 is 1. I squared is minus 1. So it gives me minus h bar times h bar is h bar squared over 2m. And then this acts first, so I take one derivative. And then I take the derivative of the derivative when this operator acts again on the result of this. So it's going to give me second derivative with respect to x of f of x. So then, as an operator, kinetic energy operator becomes what we've seen before. Okay, so now you can ask yourself, knowing this operator, can I find the expectation value, the average momentum of a particle? So if you have a particle with a given wave function, can we find its average momentum? Let's say similar to measuring position, where every time you find some value, you can measure the momentum of the particle. And every time you're going to find some value. So it turns out that the information that will give you the probability distribution of these measured momenta, and therefore the average momentum, is encoded in the wave function of the system. So, and in general, this expression for the average of x can be generalized to the average of any operator. So basically using this second structure, where first we have psi star, then the operator, then the wave function psi, then dx. Here, corresponding to position, there's an operator for the position, but because this wave function is written as a function of position, that just multiplies it by x. So it's a simple operator. There's no derivative or something like that in it. You can have more complicated operators, but average or expectation value of any operator in quantum mechanics is given by, let's say you have some operator q, it's given by the integral minus infinity to infinity psi star of x and t, the operator q, psi of x and t dx. So that's the general expression for momentum. We can write the average momentum to be equal to this integral. Minus IH bar, derivative with respect to x, okay. So this has a very nice property, if you have the average given by this expression, that for any wave function, the average momentum given by this expression, so let's call it equation 2, let's call this guy here equation 1. It's going to be 1 over mass, derivative with respect to time of the average position. Right, not that the average momentum in general is a function of time, right? It's a function of x and t. You take the derivative of a function of x and t, it's going to be another function of x and t, but then you integrate the whole thing over x, so what remains is a function of time. If you have a wave function that's evolving, at every instant, you can, with that wave function, if you had multiple copies of this, you could do measurements and find the average. But that average depends on the wave function at that instant. So for every different time, if you repeat the experiment, you would find a different average. So both average x and average p are functions of time. And then the classical relationship where momentum is just mass times velocity, quantum mechanically holds for these quantum average quantities, right? So this is something known as the Eren theorem. And we're not proving it. It's rather involved. You have to integrate by part quite a few times. So basically one can start from here, take the time derivative of this, so you have time dependence here, and then use the time dependent Schrodinger equation, do some integration by parts, etc. So you end up with this relationship. You can also turn it around, like we kind of wrote the momentum operator using de Broglie relationships and this intuition from plane waves for free particles. You could have said, well, it's desirable that the momentum operator is defined in such a way that this Ehrenfest theorem works. On average, you recover the classical relationships, and then you can start from taking this and then deriving the momentum operator, and one can do that as well. Let's go in the other way. Anyway, so that's an important relationship here. So today, so far we wrote a general expression for quantum averages, and we introduced the momentum operator, which is minus IH bar, first derivative with respect to position. All right, so the next thing I want to talk about is the notion of uncertainty. So let's review how we came up with, let's say, the original expression for the expectation value of position, right? We said we started from a discrete example of maybe having a list of people with some ages, right? And we wanted to find the average age, so we said, so going back to a discrete example, so you have some quantity. It can be age, it can be weight, it can be, I don't know, any number, height, and then there's associated probability. So let's say these take values n, right? And for each of them, there's some probability. So an example would be, I don't know, you can have a list of, let's say, 19, 20, 21, 24, and the associated probabilities are maybe 0.2, 0.1, 0.3, so 2 plus 1.4, right? They add up to 1. So one property is that sum of all probabilities should be 1, right? Another property is that the average n becomes sum over all these values n times the associated probability. So for example, let's say these are the ages of a bunch of people, that's the probability. Well, the average is going to be 19 times 0.2 plus 20 times 0.1, etc. And this comes from the fact that basically the probability is a measure of the number of people who have this age divided by the total number of people in the entire group. Anyway, so we know how to find the average, but for sure, like there's some distribution, right? We have different numbers here. And if you want to quantify how spread out this distribution is, how much uncertainty there is, like if you just report the average, what are the actual ages? How far from the average they can be? Well, you can look at the differences between the actual numbers and the average. So somehow a measure of kind of variation or uncertainty, if you just pick one of these ages, is something like this: n minus absolute value, n minus the average of n, right? So the larger these numbers are, the more uncertainty you have. So suppose, yeah, let's look at this distribution. So 19 is, let's say, 0.2, 20 is 0.1, 21 is 0.3, and 24, let's say. So that means 22 and 23 are 0, and then 24 becomes 0.3, something like this. Okay, so what is the average? Well, can actually put that into a calculator and try and find it. So let's do that. Let's find some numerical value for this average. So we have 19 times 0.1 plus 20, sorry, 19 times 0.2 plus 20 times 0.1 plus 21 times 0.3 plus 24 times 0.4, 21.7. So if, so let's say here, this is 19, 20, 21. So 21.7 is going to be here. And this is 24. So that's the average, let's say, age over here. And then, if you had a different distribution, if let's say with probability 1, everyone was 21, you would just have one of these, and then the average age would be 21, and then any age you pick, n is going to be 21 minus the average is going to be 0. So kind of, if you want to think about how spread out the distribution is, how much uncertainty there is in the age of one kind of representative sample from this entire group, well, these quantify that. Okay. But the point is, some of them are negative, some of them are positive. So for example, 24 minus 21.7 is positive. The other guys are below the average. So for them, this is a negative number. So somehow, to get rid of that, we can square this. These are sometimes negative. Sometimes positive. This is never negative, right? Non-negative. I mean, it can be 0, but once you square it, it's never negative. So if you just want to cook up one number to give you, to give you a sense of how spread out this is, you can look at the average of this quantity, right? This quantity itself depends, of course, on what n is, right? If n is 19, this is 19 minus 21.7, so that's 2.7 quantities squared, etc. But you can average these differences squared, and that gives a notion of, that gives a sense of how spread out your distribution is. So one measure of uncertainty is called variance. And basically, variance of n is just the average of this, n minus the average of n squared. So we can play with this a little bit more. You can also write this as, let's expand this out. So this is going to be the average of, if I expand this out, of n squared minus 2n times n plus average of n squared, the average of this. So the average of a constant is constant, right? I mean, this I can write if I want to relate all of these to the probabilities. I can write this as sum over n squared times p of n, right? That's the average of n squared, minus 2n average of n pn plus n average squared pn. Right? That's how we do the average for anything. We just multiply each value by its probability and sum them. And of course, the probability of like n squared being n squared is the same as n being n. Well, I mean, if we sum over all n, right, we can add them up. I mean, if you have n that's positive and negative, that's you would add both of them, right? And they multiply the same n squared. So if your sum is over original n's, that can take care of it and give you the average of n squared. Anyway, so to do this, well, the first term becomes sum over n squared pn. The second term, note that this average n is just a number, right? It doesn't depend on whether n is 19, 20, or 21. For all cases, it's 21.7, so I can factor it out from the sum. And 2 I can also factor out, so it becomes minus sum over n pn plus, again, this n squared I factor out. Note that this sum over n of pn is just 1, right? The probabilities must add up to 1. And sum over npn, sum over n of n times pn is just the average of n. So what happened here? So the first term becomes just the average of n squared. The second term is minus 2 average of n quantity squared plus average of n quantity squared. So this is average of n squared minus average of n quantity squared. So that's the variance of this distribution. This form is often more convenient to work with. So as an example, let's focus on this particular example. So the probabilities were 0.2, 0.1, 0.3, 0.4. So what is variance of n? Well, it should be average of n squared minus 21.7 squared, right, in our example. Okay, so what is the average of n squared? This is 19 times 0.2, 19 squared times 0.2 plus 20 squared times 0.1 plus 21 squared times 0.3 plus 24 squared times 0.4. Okay. So what is that? Let's just pull up the calculator again. Applications. So that's going to be 474.9 So the variance of n in this particular example is going to be 474.9 minus 21.7 squared. .01. So this of course, see, the variance is kind of, if, these things have a dimension, for example, suppose instead of just being an age that's dimensionless, let's say these had a dimension, maybe they were some heights that had some length or something. This quantity, this variance that we calculated, will have the same dimension as the quantities in that list squared, right? Because we squared the n and we squared the average. So there's another measure which is basically the square root of variance. It's called standard deviation. Which is many times shown by delta n, for example. And this is just the square root of variance of n. So in this particular example, in our example, standard deviation becomes around 2, right? Slightly over 2. So that's a good measure. See how far typically they are. It's basically like you find the average of this distances from the average squared, and then at the end you take the square roots. So this squaring kind of makes it easy to get rid of the minus signs. And this is kind of a standard way of quantifying deviations, right? I mean, you could have, for example, taken the absolute value here instead of squaring this, finding the average and taking the average at the end. That would have been a different measure. And it's not as convenient as the standard way. So this is a measure of uncertainty. So going back to quantum mechanics, we can talk about, let's say, uncertainty in position. So if I want to find a number delta x that gives me a notion of the uncertainty in the position of a particle, well, I can play the same game, right? So I can say that's square root of quantum average of x squared minus average of x quantity squared, right? So we basically like play the same game here as the discrete case. And then we already know what this is. This is integral minus infinity to infinity psi squared x psi dx. The average of x squared is going to have x squared inside the integral. And going back to some experimental setup, again, if you have one wave function and you keep measuring, every time you find your position to be somewhere, kind of like this, let's say, double slit experiment, but in some places you find like more electrons hidden in the screen. So those are regions with a higher probability, with a larger psi squared. And then some measure of uncertainty of x is like how spread out this whole pattern is. And you can find it using this relationship. So for example, if you have some kind of a distribution that maybe you have some fringes and the whole thing decays, so maybe you have some probability distribution that looks like that. And then, you're not going to find electrons with high probability over here. Somehow, well, your average is going to be over here. And then how spread out that whole distribution is gives you roughly this delta x, which quantitatively you can just get it from this expression with some integral. So the new integral that comes in is the integral of x squared times the probability distribution. Similarly, we can talk about the uncertainty in momentum, right? Because we found an operator for the momentum of a particle, and we can play the same game. We can say the uncertainty in momentum can be quantified by the average of p squared minus the average of p quantity squared. So what is the average of p? It's integral minus infinity to infinity, psi squared, minus IH bar, first derivative with respect to position, that's the operator associated with the momentum, times psi dx. So this operator just acts on psi, what comes after. P squared average becomes integral minus infinity to infinity, psi squared. The operator acts twice. So I take the derivative, multiply by minus IH bar, and then again I multiply by minus IH bar and take the derivative. So minus I squared is just minus 1. H bar twice is H bar squared, and then you take the derivative and then you act again, you take the derivative again, so that becomes a second derivative. And you've already seen this, right? This divided by 2m is the kinetic energy operator. So we can also quantify the uncertainty in momentum. We can find the average of the momentum. We can find the average of momentum squared. And we can subtract and take the square root, and that's a number that quantifies how much uncertainty there is for a given wave function in the momentum of the particle. All right, so now that we've given a precise way of thinking about or quantifying the uncertainty in position and momentum for a particle, for a quantum mechanical particle described by a wave function, I want to state a very important theorem in quantum mechanics known as Heisenberg's uncertainty principle. The principle states that, well, one particular case of it having to do with position and momentum states that delta x times delta p is larger than or equal to h bar over 2. So this principle is conceptually very important, right? So basically it means you can never know the position and the momentum of a quantum particle exactly with zero error. Any wave function you have, right? And we know any quantum mechanical particle should be described by some wave function. Any wave function you have is bound to satisfy this inequality. So the spread in position, which is a consequence of, with that wave function, you measure the position over and over and you find the particle at different places, how different the results of these observations are, gives you the spread in position, which you can quantify with this particular integral or combination of integrals. And you can do a similar thing with momentum. You can never find the particle in a situation where you know the position exactly and you know the momentum exactly. Unlike the picture we had in Newtonian mechanics, we describe the particle by their position and velocities. So for example, what happens if you measure the position of the particle very, very precisely? Well, there's this important postulate in quantum mechanics that a measurement collapses the wave function. So suppose you have this wave function which has wide probability distribution, the particle can be found in all kinds of different places. So with that wave function, if you perform a measurement, every time you're going to find the particle somewhere. And yeah, and the probabilities are given by wave function squared. But once you measure, suppose you measure and you find the particle somewhere. So suppose an electron, maybe in the double slit experiment, hit that detector, hit the screen, and there's a bright spot at one point of a certain tiny dimension on the screen. So once you measure, if you measure immediately, that's an empirical fact of nature that you're going to find the particle in the same place. So the fact of observing and detecting a particle changes this probability distribution for times that are later, right? So the wave function is something that changes suddenly upon observation. So basically anything you measure, if you measure the same thing immediately after you found the value, you're going to find the same value. So this probabilistic nature of quantum mechanics collapses after actual observation. Now, suppose you measure the position and you find the particle in a very tiny interval, so that means your wave function gets really localized. So suppose you have, so collapse of wave function. Suppose, I don't know, you have some kind of wave function like that. So you have all kinds of probabilities. You have the highest probability of finding the particle here, here, or there. But suppose, so let's say initial wave function. And then measure position, measure x, and you find some value. Let's say you find this value. So then what happens immediately after that measurement, because you're bound to find the same value again if you measure immediately, depending on the precision of your measurement. So there's going to be some tiny width because no measurement is infinitely precise, but this becomes a really high and narrow peak, right, after the measurement at that point, corresponding to the value you just measured. And this could be, you could find a highly improbable value. Like you could measure something over here. Again, all the weight, all the probability suddenly collapses to that one point. Now, this implies that now the momentum uncertainty should become very large. In the limit that delta x goes to 0, delta p should go to infinity. So you really have no idea about the momentum, right? So the momentum of the particle basically should go to, so let's say this is psi of x, let's say absolute value squared, this is psi of x. If you have some kind of probability distribution for momentum, well, here if you have this wave function, you have something similar for momentum. There's going to be some value, looks like this. When you do this thing basically becomes really, really wide. So delta p, so if delta x goes to 0, delta p basically goes to infinity. It becomes very large. You cannot go beyond the confines of this fundamental principle of quantum mechanics. Okay, so let's try to look at some examples here. Okay, so the example I want to discuss is example 5.5 from the textbook. And it says calculate delta x and delta p for the ground state of particle in a box. Okay, so how are we going to do that? Well, everything is going to be a function of the wave function. So what is the wave function? It's just a time-independent stationary state. So psi of x is going to be square root 2 over L sine pi x over L, where L is the width of the box. So here you have 0, here L, here V is 0, V is infinity, V is infinity. All right. So we know that's the normalized ground state wave function of a particle in an infinite potential well of width L. So this wave function kind of looks like that, right? It's just a sine. It's 0 here, it's 0 here. It has a maximum in the middle. It has no nodes. So to calculate delta x on delta p, we need to calculate the average of x, the average of p, and the average of x squared, and the average of p squared. So what is the average of x? That's something we should be able to tell without calculation, right? So the probability distribution is symmetric around the center at L over 2. So this is going to be L over 2. If I want to write an integral, it's going to be integral from 0 to L of wave function squared, which is 2 to the L, sine squared pi x over L times x dx. This is an integral that we can do in various ways. You can always put it into Wolfram alpha, or you can try to write sine squared as 1 minus cosine of twice the phase divided by 2, and then do integration by parts or something like that. And but basically, I mean, if we do this integral, the result's going to be L over 2, which we expect by symmetry. If I want to calculate the average of momentum, P, okay, so that's going to be integral from 0 to L of 2 over L. Then I have to separate these. So first I have psi star. This is a real function, so star doesn't do anything. So I have 1 factor sine pi x over L. Then I have the momentum operator minus IH bar first derivative with respect to position times sine pi x over L dx. So P, the average momentum, is going to be integral from 0 to L, 2 over L, sine pi x over L minus IH bar. Then I have to take the derivative of this sine function. Derivative of a sine is a cosine. The argument of sine, its derivative is pi over L. So that's the derivative. All right. So let's think about this. So it's the integral of a sine times a cosine, right? So sine basically looks like that. Cosine starts from 1, goes to minus 1. So it's an even function times an odd function, and it's going to be an odd function. The product's an odd function, so that gives me 0, right? The integral of an odd function is 0, basically around, it's kind of anti-symmetric around the center. So for any sliver over here, there's going to be another sliver over there, which contributes exactly like the negative amount as this sliver to the integral. So that's that. So basically, another way to think about it is the product is kind of like sine of twice. So we can say sine of pi x over L cosine pi x over L is 1/2 sine 2 pi x over L, which looks like something like this. So you think about the integral of that, That's the area under this curve. Here you have a positive area, here you have the same negative area, 0. One thing to remember is like the expectation value of momentum can never be a complex number. So somehow by the fact that there's a factor of I here, basically for consistency, we can't have anything but 0, right? It's going to be I times an integral that doesn't have any I in it, so that times a real number. That's a purely imaginary number, which is unphysical. So even without doing any calculation or thinking about symmetry, we could have known that this is 0. Okay, so now we have to do the more challenging integral. So if I want to calculate the integral of x squared, sorry, the average of x squared, that becomes, again, it's an integral from 0 to L. I write the weight function, so let's say 2L sine pi x over L. Then I have x squared here. I have the same weight function, dx. So this is integral from 0 to L, 2 over L sine squared pi x over L x squared dx. Again, it's an integral that we can do using integration by parts, etc., or just plug in it into Wolfram alpha. It's a definite finite integral. So the answer here to this integral is going to be L squared 1/3 minus 1 over 2 pi squared. Similarly, I can do the integral p, the integral for p squared, average of p squared. Okay, so let's write that out. Again, it becomes an integral from 0 to L, right? The wave function is 0 outside this range, so integral minus infinity to infinity reduces to this range. So let's write, I write the wave function, the complex conjugate of the wave function, which is the same as the wave function because it's real, times minus h bar squared second derivative with respect to x times the wave function. Okay. So how should we proceed? Well, I can factor out these constants. So I get 2 over L minus h bar squared. So I factor out this, this, and that. Then I have integral from 0 to L sine pi x over L. Let's take the derivatives one by one. So I have the first derivative of the derivative of that, which is going to be pi over L cosine pi x over L. So I just take one derivative of this function sine of pi x over L. Sine has a derivative that's cosine, and then the argument of the sine is a linear function of x, so the factor of pi over L is the derivative. Okay. Let's carry all of these, and I factor out this pi over L. Again, I have sine pi x over L. I want to take one derivative of this cosine. The derivative of cosine is minus sine. So I get another factor of pi over L from the argument of the cosine, and then the minus is because the derivative of cosine is minus sine, and then I have sine. So minus 1 kills that. So we have 2 pi h bar squared over L cubed, right, by factoring out, and 2 pi squared, 2 pi's, pi, L cubed, integral from 0 to L of sine squared. And this integral, that's a simple integral. We can convert maybe sine squared to cosine of twice the phase. So this turns out to be L over 2. So our result becomes pi squared h bar squared over L squared. Okay, so that was average of p squared. So delta p is the square root of p squared average minus average of p quantity squared. This was 0, so we don't worry about it. So it just becomes the square root of that. If I want to calculate delta x, it's going to be the average of x squared, which was just calculated. So it's L squared 1/3 minus 1 over 2 pi squared. So minus the average of x squared. So let me just write the general expression here again. So this is this, and average of x was L over 2, so L over 2 quantity squared. So it's going to be square root of, factor out an L squared here, I have 1/3 minus 1 over 2 pi squared minus 2 squared is 4, so 1/4. That's going to be, that is going to be, yeah, I mean, it's not very illuminating. It's going to be some number. So I factor out the L and it's just some number. So it turns out numerically it's 0, 1, 81 L. And then finally we can check delta x, delta p, which is, so the L's cancel out. It's going to be this number times pi times h bar. Pi is 3.14 something, so that's like 0.57 h bar. So it's a little bit more than half of h bar, and it satisfies the Heisenberg uncertainty principle. It doesn't go below h bar over 2. All right, I think that's a good place to stop. So we'll continue this discussion in the next lecture. And very soon we're going to move to higher dimensional systems and talk about things like the hydrogen atom, which basically follow the same kind of general structure but applied to higher dimensions.